Hello friends, in this video for chapter DC circuits, we'll be discussing about three topics: ammeter, voltmeter and galvanometer. As the name suggests, ammeter or ampere meter is a device to measure current, and it is denoted by this symbol. Similarly, voltmeter is used to measure voltage. It is denoted by a symbol V, and it measures voltage. Galvanometer is different from ammeter and voltmeter in this respect that it does not measure anything. It only detects presence of small current. So it detects current, and which is of the order of milliamperes. Galvanometer is denoted by symbol G. So but why do we need ammeter, voltmeter, galvanometer? Because till now we have been using different analysis techniques to analyze different circuits, because till now we know the parameter values of all the resistances, all the EMFs and batteries. So it was quite easy for us to use them in either KCL or KVL and find out the different values of currents and voltage differences. But now we are considering a situation in which we are given a circuit and we do not know what is the value of a resistor and what is the value of the battery inside it. And we need to measure a current in a branch or a potential difference across two terminals. Then these ammeter, voltmeter and galvanometer devices, these come handy for measuring unknown values in a given circuit. So we'll just go through a couple of examples in which we'll see that how ammeter and voltmeter are applied and what are the resistance characteristics of these devices. So while adding these devices onto an existing circuit, we know that we need to follow the series or parallel combination rules which we have studied in the previous topics for this chapter of DC circuits. And we know that while considering the series and parallel combinations, we need to abide by the laws and properties which we have already discussed. So let us see, and let us start with ammeter. So we know that ammeter is used to measure the current. And now let's say in a given circuit, we need to apply ammeter. So what can be the best possible combination to use ammeter? It can be either in a series or in a parallel. So let us assume that there is a branch A, B, and I need to measure the current which is flowing in this branch, current I. So the best possible combination of ammeter should be in series in this branch. Why? Because we already know that in a series combination, all the elements which are added in a series, the same current flows through all of them. So ammeter use this principle and takes advantage of it to find out the value of the current which is flowing through it. Similarly, in case of a voltmeter, if we are given two terminals A and B, and we need to measure the voltage difference between these two, and let's say in between these two terminals we have a box kind of thing in which there are multiple elements or like resistors, cells, or all those things, and we do not know about all of these. So the best way to measure the voltage between A and B is to apply the voltmeter in parallel with them, because we know that in a parallel combination, all the elements which are applied in parallel combination across two terminals experience the same voltage difference between them. So voltmeter takes advantage of this thing. Now going to the characteristics of ammeter and voltmeter, because these are practical devices, so they have a resistance associated with them. So the resistance of the ammeter, we'll call it as RA, and the resistance of the voltmeter, we'll call it as RV. But let us consider this possibility that I have applied an ammeter in a series. The ideal thing for me would be that ammeter has a zero resistance, because I only want to measure the current and I don't want that the current should feel any resistance. So the original current which was flowing before addition of ammeter should remain same even after applying the ammeter. So I can define the property of an ideal ammeter. So ideal ammeter has resistance 0. And we have already established an understanding that ammeter is only applied in series with the desired branch or desired terminals. Similarly, for voltmeter, we know that we are applying it in a parallel combination, and let's say this current is coming here. So similarly, for voltmeter, we do not want that the voltmeter should attract any current towards it. So the current which would be going through this resistor and was giving a potential difference would tend to change if we are just introducing a voltmeter with some finite resistance. So we need that, okay, the current should not enter into this branch. While in case of ammeter, we needed that the current should always flow through that branch without any resistance. So in case of ammeter also, in case of voltmeter also, we can establish an ideal characteristic, which is so the resistance of the voltmeter ideally for us should be infinity, so that it does not attract any current and the potential difference between A and B terminals remain unchanged. So we can also look at all those things in an easier way, is that whenever we are given an ideal ammeter is in the circuit, so we can directly write this like A, B, and we can just replace the ammeter with a zero resistance wire, because we know that, okay, ideal ammeter has a resistance of 0, and we can write ammeter just beside the zero resistance wire. Similarly, in case of voltmeter, I know that I need to measure the potential difference between A and B. So what I can do is that I can just make it as open circuit here and write voltmeter here, because I know that a broken and open circuit has a characteristic that the resistance is infinite between the two terminals. Next thing I can see is that, let's say if the ammeter or voltmeter has some finite resistances. So in case of ammeter, it's not 0, and in case of voltmeter, the resistance of it is not infinity. So let us take an example. So this is a circuit which is given to us. Ideally, or in the practical purposes, we would not know what are the resistance values, but because we are forming a question for us, let us say we'll know all the parameter values, and we'll analyze both the cases for ammeter as well as for voltmeter. So let us say this is 6 volts, this is 2 ohms, and this is 2 ohms. So now we know that the current which is flowing in this circuit would be 6 volts upon, because these two are in series, 4 is 1.5 amperes. So this is the current working of the circuit when I have not applied any ammeter or voltmeter. So let us say I need to measure the current which is going in this branch. So let's say I am naming the branches. So I need to measure the current which is flowing in branch EB. So what I'll do is that I'll introduce an ideal ammeter first. So because I'm introducing an ideal ammeter, I can replace it with zero resistance wire, and I can write just A above it. So the ammeter reading, A1 would be 1.5 amperes. It was easy, it was quite easy to understand. Similarly, let's say I want to measure the potential difference between A and E. So I would be applying an ideal voltmeter between A and E. So let's say this is an open circuit, and I am just applying a voltmeter. Because we already established that thing that a voltmeter can be replaced by an open circuit due to its infinite resistance in its ideal state. So now we need to measure the potential difference between AE, and the reading of the voltmeter V1 would be IR. So I is 1.5 amperes, 2 ohms, so that means it's 3 volts. Now let us consider a second case in which the ammeter and voltmeter are not ideal. So in this case, if I am putting my ammeter at the same location between E and B, then it would introduce some resistance, and let's say I have been given that the RA or the resistance of the ammeter is 2 ohms. So now I have, this is 2, this is 2, this is also 2, and this is 6 volts. Now I can calculate the new current which is flowing in the branches, which is I dash. So I dash is 6 volts. So before that I should write A above it because it's a ammeter location. So I dash would be 6 volts upon 2 plus 2 plus 2, that's 6. So it's 1 ampere. So now the new reading of the ammeter, which is A2, is 1 ampere. So you can see that the ammeter which we are using right now is not an ideal ammeter. That's why it's influencing the current reading which already was there in the circuit. Similarly, like in the previous example, we are trying to measure the voltage between A and E points. So A, E, and for now let me just remove this ammeter, and because now we are only concerned with measuring the voltage. So now it's been given that RV, or the resistance of the voltmeter, is 2 ohms. So I'll be applying the voltmeter in parallel with points A and E. This is 2 ohms and this is V. And this I dash will become I double dash. So I can calculate this I double dash, like it's 6 volts, and the net resistance would be 2 parallel with 2, that will give me 1 ohm, and then 1 ohm in series with 2 ohms, that will give me 3 ohms. So it's 2 amperes. And I can measure the potential difference between A and E by I into R. So the new reading of the voltmeter V2 would be 2 amperes into 2 ohms, that's 4 volts. So as you can see, the potential difference, which earlier was 3 volts, now has been changed to 4 volts. Although the change in magnitude is very large, seemingly like 25%, at least 33% has increased, it's because we are considering the resistance of the voltmeter in of the same order of the resistances which are already present in the circuit. But it's totally possible that in the practical applications as well, you are using an ammeter or voltmeter which have resistances which are of the same order as of the resistances which are already there in the circuit. So these are the analysis of voltmeter and ammeter which we have discussed, in which we considered that okay, they can be ideal, like with resistance 0 and resistance infinity, and they can be non-ideal, in which they will be influencing the circuits. Now let's come on to the third device, which is galvanometer. As we have earlier as in the starting I just mentioned that it does not measure anything, it only detects the current, and also of the order of milliamperes only. As you can see that in case of ammeter, we did not have this fear of that okay, the ammeter cannot sustain up to high amperes, and we were freely using it up to 1.5 amperes, 2 amperes. So there is a certain rating associated with each of these devices, up to which they function very nicely. For ammeter or voltmeter, they can be up to certain amperes or certain volts, but for a galvanometer, it's only up to certain milliamperes. So there is a current rating associated with the galvanometer, which is known as Ig. So it is the maximum current which a galvanometer can show. So what happens in a galvanometer is that there is a needle, and there are certain markings, and the deflection of the needle shows the value of the current that has been flowing through the galvanometer. So let's say if this is 0 and this is x, so there are like x divisions between them. So each deviation or each division represents some milliampere, like 0.5 or 0.1 or 1. And let's say if there are 20 or 30 or x number of divisions, then we can define the full scale deflection of a galvanometer. So this current is also referred to as the full scale deviation current, or full scale deviation or deflection, because it is the current which is shown by the galvanometer when the needle is fully deflected. But if the current flowing through the galvanometer increases and go beyond Ig, then the galvanometer is like badly hurt and it cannot function anymore. So the only principle we need to take care while using a galvanometer is that the current flowing through the galvanometer should not go beyond Ig. The galvanometer by its own characteristics has a resistance associated with it, which is referred by the symbol G, or like not G with a circle but only by G. Another property of galvanometer is that it can be modified a little bit by adding another elements to either work as an ammeter or voltmeter, and let's see how it can do that. So let's say I have a similar kind of situation in which there are two terminals A and B, and there is a branch connecting A and B, and I need to measure the current which is flowing in this branch. What I can do straightforward is that I can introduce a galvanometer. But what will happen if this I is much greater than or just above a certain threshold of this Ig? The galvanometer will break down and it will not be able to function properly. So what can we do? As I earlier told you that the main property of the galvanometer which we need to take care is that only Ig should pass through galvanometer. So what can we do is that we need to divert the rest of the current through some other resistance, and it can only be diverted if the other resistance has a resistance value lower than the galvanometer's resistance. So let us modify the circuit a little bit. So this is my galvanometer's resistance, and now I am applying a different resistance in parallel with galvanometer, and I am calling it as Rs, and this resistance is known as shunt resistance. So now what will happen is that this I will come, but only Ig will go through galvanometer, and the rest of the current, which is I minus Ig, will be going through this shunt resistance. In this way, the galvanometer remains with proper functioning, and also because the Rs is selected by us, we are able to measure this I as well. So we can see that because these are in parallel combination, the voltage difference across these 2 points will remain same between the galvanometer and between the shunt resistance. So I can write that Ig into G equal to Rs into I minus Ig. So in this equation, Ig is known to us because we have purchased the galvanometer and we are the ones who are implementing it. We know the galvanometer resistance. We know the shunt resistance because we are implementing it. We know Ig. So the only unknown in this equation is I. I is the current which we want to measure. So through this circuit, the galvanometer is converted into an ammeter. Similarly, let us take one more example or take one more configuration of galvanometer in which we are again given two terminals, but now we are interested in measuring the voltage between them. So we want the galvanometer to act as a voltmeter, and let's say we are again attaching the galvanometer through it. So let me replace it with the galvanometer resistance. But now what will happen? Again, because there is a constant voltage difference which is present between A and B, which let us call it as V, the galvanometer will experience some current flowing through it, and this current will definitely be greater than Ig. So this I will be greater than Ig because the I would be V by G, and if it happens that the I is greater than Ig, then the galvanometer is is like prone to breaking down. So what we'll do is that we'll introduce another resistance, so that this resistance, when in series with the galvanometer, would come in this equation, and the new I dash would be V upon G plus Rs. So it would decrease this I dash, and this I will become I dash. But you know that we do not want I dash to be any value. We want I dash to be specifically less than Ig. So let us say that if I dash is equal to Ig, then then we know that okay, V would be G upon plus Rs. So this equation, in this equation we know G, we know Rs, because it's still called the shunt resistance, and it is added by us only, and the V is the potential difference between points A and B. Ig is known to us, G is known to us, so effectively we can find out the voltage difference. And this is the conversion of the galvanometer to a voltmeter. So galvanometer, although directly it cannot measure any current of ampere values or any voltage of any volts value, but itself it has a very small property that it can detect small currents. It can detect whether some current is passing through the circuit or not, and using its two characteristic properties of the maximum current rating and its internal resistance, we can turn it into either an ammeter or a voltmeter by adding another shunt resistance to it in parallel or in series. So in this video, to sum up, what we discussed was that ammeter and how does it measure the current by being in series combination. Also the resistance which is associated with an ammeter, and an ideal ammeter should have a resistance of 0. Similarly, a voltmeter and how it is applied in parallel to the existing circuit to measure the voltage across two terminals. An ideal voltmeter should have a resistance of infinity, so it should not affect the existing voltage or the existing current in the branch. And in the end, we discussed how a galvanometer can be turned into an ammeter and voltmeter and can be really useful.